Hello, everyone. Thank you for joining this RISE Masterclass on insulation and ventilation. My name's Alex Kramer-Smith, and I'm a junior sustainability consultant at Turner & Townsend. We're joined today by Julian Boss, a principal consultant, also from Turner & Townsend. Just so you're aware, this is a retrofit information support and expertise event, which is fully funded by the Department of Energy Security and Net Zero, delivered by TNT. I'll now hand over to Julian to start today's presentation.
Thanks, Alex, and welcome everyone to, as Alex said, this presentation on insulation and ventilation. I'm going to just put my camera off there. I can't actually see anyone else on the screen while I'm presenting. I will take any questions at the end of the presentation. But as Alex said, we should have plenty of time for discussion. So basically, insulation and ventilation, this is quite a high level presentation, really kind of outlining the basics, but the importance of the relationship between insulation and ventilation. So that's basically what we're going to be covering today. Why do we need insulation and ventilation, the types of insulation that we'll be thinking about in terms of retrofit, types of ventilation that you're likely to be thinking about, and a few slides about the kind of risks of what can go wrong. So first up, why do we need insulation? So basically we're talking about typically, well, older homes, so pre-1920s homes, generally solid wall design without any kind of insulation facility within the walls. Generally, the ventilation is done through drafts and air bricks that are provided within the actual fabric of the building. And typically those homes were heated with open fires, and they were providing a kind of draft to draw in fresh air through the rest of the house. So in terms of more modern homes than that, we typically still don't have an awful lot of provision for insulation. Cavity walls were really about trying to keep the outer skin of the wall with like a rain screen, keeping the inner skin of the wall dry, which did improve the thermal efficiency of the walls, but there was no provision for any kind of insulation within that cavity at the time when they were constructed. Certainly, the early, up to about the 1950s. So there are ways that we can improve the energy efficiency of these buildings. And in doing so, also we're considering the thermal comfort and looking at reduction of the energy bills and also the carbon emissions associated with the energy use for heating. Insulation ends up being really a sort of fundamental part of the improvement to the fabric of these houses that we're talking about. And really the counterpoint to this is ventilation. So we're looking at indoor air quality. And where you were thinking about the older homes, naturally ventilated, i.e. plenty of drafts. Once you're improving the air tightness of those properties by putting insulation on the outside or the inside of solid wall homes, or filling the cavities of cavity wall homes, changing windows, external doors, and that kind of thing, you are reducing the gaps and holes and cracks around windows and doors and everything else, and you're improving the air tightness of that property. But in doing so, you're kind of reducing that background ventilation. In the second point there, ventilation is basically providing fresh air, so good quality air for the occupants. And when you're ventilating a home, you're basically ventilating stale air, which is got a buildup of moisture from washing, cooking, respiration, CO2 from respiration as well, and VOCs, volatile organic compounds, which are emitted from all sorts of different things, curtains, furnishings, carpets, paint. Lots of different materials that we have in our homes are emitting various levels of chemicals that are used in their finishes. So the last point, very important, ventilation is not really an optional extra in all of this, because PAS 2035, which is the kind of retrofit methodology which we need to follow if we're doing any of the government-funded domestic retrofit, that requires that homes should be adequately ventilated. And at the bottom there is a kind of retrofit catchphrase: build tight, ventilate right. Basically meaning if you're going to reduce the air leakage of a building, then you have to provide adequate ventilation to maintain the indoor air quality. So when retrofitting a home, the air tightness of the property will be affected. And as I've mentioned, when we're changing things, when we're doing things to the walls, we're maybe putting external wall insulation onto a solid wall home. We might be introducing new windows as well. And in the process of doing this, we're going to be looking at making sure that we're reducing the uncontrolled ventilation, the draft, the kind of background air change that most homes have got to a degree. If you think about circumstances where you have, in the summer, that's not a problem. You want some background ventilation. It's not going to be something that's creating a problem. But in the winter, if you have very cold weather and a strong wind, that will be sucking your warm air out of the house and introducing very cold air into the house, and that's going to be wasting a lot of energy in terms of the heat loss. So when you're thinking about the reduction of that heat loss, creating a warm environment which is more affordable to heat, then you have to be at the same time considering introducing some sort of ventilation regime to make sure that you've got, you're maintaining this indoor air quality, and you're not going to create more problems by having reducing the quality of the indoor air. So if we're increasing the air tightness, we can have significant impacts on that air quality. And actually, we're very well aware of the headlines that have been in the press lately of health impacts to residents, particularly of issues like mold created when you've got excess condensation happening in homes where it has, the ventilation is particularly poor, and you have high levels of indoor moisture. So just moving on to types of insulation. So we're just going to talk about these 5 main types of insulation: loft insulation, floor insulation, less common, but very kind of effective. Cavity wall insulation, probably the lowest, well, you've got loft insulation, cavity wall insulation, the kind of low-hanging fruit of those, if you like. External wall insulation, so that's where you're putting an insulation layer on the outside of typically solid walls, but it could be a cavity wall if the cavity is very narrow, and whatever you can fill that cavity with is not really enough to give you a good thermal performance of the wall. You might do cavity wall insulation into a narrow cavity and some external wall insulation. And then the last one, internal wall insulation. So installation of fiberglass or mineral wool to a depth of 270 millimeters. So that's typically most lofts will have 100 mils of insulation, which is basically the depth of your ceiling joists. They're normally 4-inch joists and the insulation that's pretty much standard would be to the depth of those joists. So we're really looking at 170 mil on top of that. So airflow must be maintained in a loft space. So basically this is maintaining a fresh air flow across a building from the eaves, across the eaves. So basically when you're installing that loft insulation, you don't want to be installing it right up to the inside of the rafters or under the felting. It does need to have a small air gap there to allow for air movement in the loft. Same reason as we're talking about ventilating in the house itself, to avoid buildup of moisture. Moisture can lead to condensation and damage to the wood structure in lofts, which again, to be avoided. And just that last point, this is the cheapest and most effective insulation measure in terms of the reduction of heat loss. We're talking about sort of about 20% roughly heat loss through the lofts of a building. So actually, in terms of the cost of the material, it's a sort of measure which could be done, as I say on this first bullet point here, by a competent do-it-yourself kind of resident or contractor. It's a straightforward job, not technically very difficult. Some of the cons for this measure really are about what lofts tend to be used for. So quite often they're full of belongings that people don't want to get rid of for whatever reason, long-term storage, because the space is also quite dusty. Generally it's a big hassle in terms of emptying the space in order to be able to top up your loft insulation. And that actually is quite a difficult thing. It's quite a challenge for people, a bit of a hurdle to think about emptying lofts in order to actually put insulation in there. It can be quite an inconvenience and quite a disturbance. And that last point there, sometimes that can be quite a hot and uncomfortable task to complete if you're doing it in the summer, which I would not recommend. Quite often with those loose fibrous type materials, then you do, have to wear gloves and masks as well. It's not a pleasant job. But as I say, it's a very good value way of reducing your heat loss if that job is available to do. Next up, we got floor insulation. So this is really looking at ground floors. And the image on the right there is where the typical kind of floorboards have been lifted, and insulation in that instance, probably PIR type insulation foil back there, has been installed between the floor joists, and then there'll be an airtight membrane also introduced there just to stop the any air moving its way around the joists and up through the floorboards. But typically that insulation has to be fitted pretty tight to the joists as well. I think in that instance as well, you can see at the back of the photo what looks like possibly underfloor heating is being installed there. But anyway, the silver material here is the insulation, and then the floorboard would be refitted on top of that. You can also do this with concrete floors. So if you've got concrete floor, typically in a sort of rear extension of Victorian houses, can have a concrete floor there. It's a bit more of a disruptive job in the sense that you're really, if you've got a floor which hasn't got insulation underneath the actual concrete screed, you need to break that up, remove it, and then redo the floor. As I can say there, it can be installed in most properties. If you're working with suspended floors, you basically need to be aware to maintain the airflow under that floor. So at the same time, checking that there's no obstructions to the air bricks. So basically what you're doing is you're separating the flow of air under the floor from being able to leak back into the property above. So you have an airtight membrane with your insulation, and then the floor is installed back on top of the joists. Residents do say that actually because there's quite a sensitive awareness of temperature difference between your head and your feet, actually having cold feet due to low temperatures and ground floors, it makes quite a big difference to your perception of comfort. So it's definitely a measure that which, it has a noticeable improvement on resident comfort. Some of the pros and cons of this, though, there we go. That first point on the pros: improvement of thermal comfort for occupants, especially in homes with maybe smaller areas of carpet or no carpet at all. Helps create this thermal envelope around the house, so that's maintaining the kind of insulation layer. And those kind of points against, it is very disruptive. You're having to empty a house, you're taking up carpets, other floor coverings, removing the floorboards, etc., etc. It's quite a disruptive process, very labour intensive. Although there are some installations now being done by the sort of underfloor robotic devices, U-Bolt being the most well-known one that's around at the moment. We've got their costs are significant because of the sort of labour intensity, looking at removing furniture and obviously replacing probably a number of the floorboards. When you lift them, they don't tend to come up in an easy way. Quite a few are always damaged, and so you need to be thinking about the cost of that. Same for skirting boards. The other problem is you can expose other issues, which might be to do with the condition of wiring or plumbing, or maybe you're going to discover other issues around some sort of maybe subsidence or structural issues, which, again, good thing to fix them. You wouldn't necessarily expose them. They wouldn't necessarily cause a problem unless you happen to be lifting the floor. So it tends to be the case that when you're doing this kind of work and exposing parts of a building which are not readily accessible, you're always obliged to fix everything that you find there that needs attention. So cavity wall insulation. This is the most common type of installation that you're probably aware of. So we're really looking at properties since about the 1930s. Cavity wall insulation, probably the standard. Involves filling the cavity between the inner and outer layers of the wall with a blown insulation material. This can be polystyrene beads, or it can be a sort of blown fiber material like a mineral wool. And you can see in the picture on the right there, that's the typical way that that's installed. So this reduces heat loss through the wall by creating an effective thermal barrier between the two layers of block and brick wall layering, and you're basically creating a thermal barrier which will trap the heat inside the building, and that will make the building more comfortable and energy efficient. Some of the risks around this are that you need to do a very good survey of the wall before you introduce material in there. The other thing is that quite often these walls, where they have been filled with material previously, there's a lot of instances where water has got into the cavity, and because the material is kind of maybe a sort of porous fiberglass material, it's soaked up the water, and it actually then ends up almost creating a sort of wet barrier, which creates problems. So when you're trying to replace the failed insulation in that situation, actually what you need to be thinking about is having the material removed, letting the wall dry out completely, then fixing whatever kind of holes or other kind of entry points the water has before you refill it. Otherwise, you're just going to create the same problems again. But as I say, the actual introduction of the insulation material into the wall is not an expensive job, but it does need careful surveying to make sure that there are no other issues that you're kind of building into it. So here there are a few pros and cons. Easy to install than other insulation, cheaper, and gives you a better bang for the buck in that sense. It's you can obviously only do it where you've got the opportunity, you've got the right a decent cavity, and there are no other issues in there. It's a pretty straightforward job. So usually results in good reduction of space heating demand and reduction in associated reduction of energy bills. Points against it are really to do with the condition of the walls. And as I say there, if the cavity is 50 mil or less, that's too narrow to really be on its own enough of an improvement. You need to be thinking about some sort of other solid wall type, internal or external insulation to, in effect, pop up the cavity when it's a narrow cavity. Always got to deal with any existing issues, failed cavities. And there is this last point there that for detached homes, it can be quite an involved job, and certainly not as expensive as external wall insulation or internal wall insulation, but the prices will be obviously considerably more when you're dealing with a sort of larger detached property. EWI or external wall insulation. What we're talking about here is where you're attaching a layer of insulation material to the external wall of the house. It would be a kind of graphite polystyrene board, or it could be a system which includes maybe a mineral wool, something like a rock wool material. And quite often this would be a system in the sense that you would have a layer of insulation material and then a mesh layer, and then you would then finish off with some kind of render material on the outside, which would then be painted, or it might even have a coloured render included in that. So this is creating a thermal barrier that keeps the heat inside the building, again, reducing the amount of heat escaping out through the wall. And move on to the pros and cons of this particular measure. So first point there, it's one of the main options for solid wall properties, except where you have the building listed or in a conservation area, whereby that outside appearance of the wall, maybe the brickwork finish, or it might have some sort of ashlar or stone finish, is seen as culturally important and is to be protected. Therefore, you've got to look at insulating inside. Often with this kind of situation, you might have what's called a hybrid approach, where you would do the front of the property internally, insulate internally, and the back of the property where it's unless the property is listed, maybe a conservation area, though if it's a conservation area, you could probably do external wall insulation at the back. If the property is listed, it will unlikely to be allowed it at in any part of the property, so you'd be looking at internal. If that was permitted, given the importance of internal features on certain listed buildings as well. So it's really a case of looking into the kind of conservation details of a particular property. Where it is permitted, one of the benefits can be the improvement of the visual appearance of a building, basically because you're giving it a new clean finish. It usually offers very good reduction in space heating demand. Again, because you've got a very significant amount of heat is generally lost through the walls. So if you're able to reduce that by a significant amount, then it's going to have a big impact in your energy bills. And most systems have a 25-year guarantee as standard. The cons with this particular solution: conditions of the walls, other damp issues must be addressed before you install, obviously, otherwise you're kind of trapping those issues within the insulation layer, particularly anything to do with damp or water intrusion, rising damp, or any other kind of issues maybe to do with rainwater goods or leaking pipes or anything like that must be sorted before you, and allow the wall to dry out before you start introducing solid wall insulation. So it does require a considerable amount of ancillary work. It's expensive, relatively. I mean, it's more expensive than cavity wall insulation, but it requires a certain level of maintenance, in the sense that you have to be careful not to damage the walls. It's the outside finish will need to be maintained just the same as any rendered finish will need to be maintained. The last point is important there, that the windows where you're introducing external solid wall insulation should be moved into the insulation layer. So that's the windows, presuming that those windows are double glazed, ideally treble glazed, but the windows should be moved out from being mounted in the brick and then be moved into the insulation layer, because that eliminates the cold bridge that you would get around the window, so where basically heat can still escape around the edge of the window frame if the window is still mounted in the brick. Just moving on to internal wall insulation. So this is where I mentioned that if you can't insulate on the outside of a building because maybe you're in a conservation area, you'd be looking at an internal insulation. And you can see on the right there, that's an approach where you batten the wall and then have your insulation panels between the battens, and then you would mount plasterboard on top of that, replaster, and then decorate. So this basically creates a thermal barrier, reducing heat loss and keeping the heat inside the building. As it says there, walls are typically stripped back, insulation boards added underneath a new plasterboard. And again, this is one of the very common solutions for solid wall properties. Generally, where we're thinking about this kind of solution, you have to be careful about the materials you're using, because what you've got to bear in mind with older properties is that the solid wall properties they're made of materials which really got quite cold and damp in the winter, but then dried out in the summer. And what we want to really avoid when you're introducing layers of insulation on top of these type of walls is to trap moisture in the wall. You basically need to avoid doing that. So you need to have what are called thermally open materials for solid walls, whereby you're allowing any moisture which might get into the wall to freely migrate out again. So that's something that the retrofit designer will be looking at carefully in terms of specifying this measure. Some of the pros and cons for internal wall insulation. Good option when planning or physical circumstances prevent alteration to the exterior, as I mentioned. Usually offers good reduction in space heating demand, helping improve fuel bills and resident comfort. Can be done one room at a time to minimize disruption. So literally, as and when you might be looking at redecorating rooms. As it says there, you basically can think about this as a one room at a time solution, stage solution, and it's so typically cheaper than EWI. I would say that depends. Some of the situations you might find where you're having to maybe move sockets and radiators, and maybe some of the detailing of a particularly ornate woodwork or ceilings or something like that, those can add to the cost of IWI. So typically cheaper if it's a straightforward, and not particularly decorative room. That might be true, but I would say that it's not always the case. So on the con side, we've got condition of the walls, damp issues must be addressed, pre-install, and risk of condensation if poorly installed. Yeah, they do require a fair bit of ancillary work because obviously you're looking at removing of skirting boards and carpets and various other materials, which butt up against the external wall, and where you're going to be reducing room sizes by typically 100 mil, 75 mil to 100 mil on the inside, unless you're using quite costly materials like aerogels, which can be used in certain circumstances and may, in fact, because they're very high performance and thin, they reduce the amount of ancillary work you need to do. So again, that can be worth considering. So the last point, adverse effects on airflow and water vapor movement. So as I mentioned, when you're working on these solid wall homes, you really do need to be thinking about that kind of moisture open materials to allow for the migration of any moisture that's in the wall, maybe even trapped in the wall. That it's difficult if you're retrofitting properties in the kind of colder winter months to be able to say, well, the wall's dried out. It's 99% of the time probably not dried out. So you do need to have the materials you're using will allow a wall to dry out. So just moving on to different types of ventilation. What I should say actually is there is a building regs part F, which covers ventilation requirements. It's quite a vague document in the sense it talks about things like adequate ventilation, which of course is dependent on level of use, number of occupants, age of the occupants, and all this type of stuff. So you do need to be thinking about a lot of the variables that we have with all homes and living situations and the different sort of stages of life of the occupants. So yeah, ventilation is very much something which is not a one size fits all situation. But so just thinking about the types of ventilation, we've got intermittent extract ventilation, which is kind of typical of what you would have in most homes that you come across, where you might have extractor fans in kitchens and bathrooms, and maybe some trickle vents in windows, and that would be your intermittent extract ventilation strategy. Passive stack ventilation, mechanical extract ventilation, and then mechanical ventilation with heat recovery. Intermittent extract ventilation, the illustration being there with the kitchen hood. Points here being made an option for leaky homes as it relies on background ventilation by drafts. So you would always have, as a fan in the kitchen, extract fan in the kitchen is working, it would be creating low pressure in the kitchen and drawing fresh air from, whatever rooms that are nearest, or windows or doorways, generally drawing in fresh air, because it's creating low pressure in that area. next point on there is intakes are typically through trickle vents in windows. So that is a common kind of counterpoint to the extract ventilation, is that you would have the trickle vents open, just allowing for that kind of background ventilation in most rooms. Cross ventilation occurs between rooms, and that's via door undercuts. That's quite important when you're thinking about the air tightness of a building after you've insulated the walls and maybe put new windows in, is to have doors which aren't very tight to carpets, that actually when they're closed there is a chance for air to move under doorways between rooms. And that last point there, yeah, typically we would have extract fans which operate when you switch a light on in a bathroom. Sometimes those are activated by humidity switches. So when the humidity of the room gets to a certain level, they would boost and extract more moisture until that humidity level drops down again. But in most instances, they're just on a timer. It might switch off after 3 or 4 minutes after you switch the light on. Sometimes those extract fans might be operated on a PIR, which is a motion sensitive thing as well, so that they know someone's been into the bathroom. They might switch on by that trigger as well. And you can get, different switches fitted to a lot of these different extractor fans now, which might cover all of those things. So it could be humidity controlled and PIR controlled and electrically controlled off a light switch. So passive stack ventilation, this relies on the stack effect, and where you would have a pressure difference between, the ground floor situation and the top, and typically the top of a pitched roof. You also get a pressure drop of any kind of wind blowing across the ridge. So this is kind of using those pressure differences to extract air from moister areas like bathrooms and kitchens, and then that extraction will draw in fresh air through the trickle vents around windows. And you can see from the illustration there, that fresh air will migrate through the house through door undercuts typically. So mechanical extract ventilation, kind of doing the same thing, but through a powered extractor fan rather than relying on passive stack. Typically, these would be running kind of constantly, but on just a tick over level, if you like, but with sensors in bathrooms and kitchens to kind of boost as the moisture levels, humidity levels in those rooms increase when they're being used. Same thing, fresh air is being supplied through trickle vents in the habitable rooms, cross ventilation between rooms via door undercuts, and that last point, it could be centralized or decentralized. Basically, yeah, the centralized is where you have a single fan with ducting in the house going to the wet areas, bathrooms and kitchens. Or you might have separate units in the bathrooms and kitchens which are operating on that same manner. So they're on kind of constantly on a tick over level, and then they boost as those rooms are used and the humidity levels increase. And finally, on the ventilation side, we're looking at mechanical ventilation or heat recovery, or MVHR as it's referred to commonly. It's only really the sort of measure we'd install in a very airtight property. Basically, because what it does is it extracts and supplies the air. So what you don't want is fresh air coming in through leaks in the building. So basically, the principle of it is that it has a single unit, a single heat exchanger with ductwork, basically providing fresh air to the living rooms and extracting from kitchens and bathrooms. That warm, moist air from the kitchens and bathrooms goes through the exchanger, and the heat from that is extracted and used to preheat the fresh air coming in. And that fresh air, that warmed fresh air, is supplied to the bathrooms, the bedrooms and the living rooms. So you can see it kind of operates very well in a very tightly sealed house, because it relies on the fact that you're not getting fresh air leaking in around windows and doors. And the typical kind of air tightness that you need to be aiming at is about 3 cubic meters per hour at 50 pascals pressure. That's if you were running a kind of pressure test on the house. That would describe a level of air leakage, and that you need to be at that level or lower, really, to be able to use an MVHR system properly. That last point, it says always centralized. You can get MVHR, single room MVHR units, actually, where, within the one unit, say within a kitchen or within a bathroom, it's supplying fresh air as well as extracting stale air, and that the air that's coming in is preheated with the warmth from the extract air. But they're only really working in that localized way. So you're not, in the centralized way, you're not providing a constant supply of fresh air to the living rooms, which is why a centralized MVHR system works very well. And they're pretty much always used with passive house properties. So this is the passive house is the German sort of very low energy building standard, which specifies high levels of insulation, very high levels of air tightness, and ventilation provided by MVHR units. Moving on to the last section of the presentation. So really, what are we trying to avoid? Why are we so keen to get this to maintain, keep a close eye on quality of installation and design? So when basically a lot of the time you think about retrofit, you're thinking, of insulating tower blocks or blocks of flats or all sorts of different kind of properties. But over the years of the various funding streams, there have been a significant number of projects that have been done at pretty low quality levels of installation, let's say. And one of the most notorious ones is this project in Flitwick in Preston in Lancashire, completed under CESP, which was an earlier government funding scheme. And basically the installation work was carried out by, my understanding of it was done at the very last minute. The project was pushed through to be able to be eligible for the funding. The installation work being carried out by subcontractors was rushed through, so people were really not given proper training, and the poor quality installation work combined with a lack of addressing ventilation issues allowed for problems all over the place. So you've got water being trapped behind the insulation layer. You can see in that top left image there, the eaves, so where the guttering is above the insulation layer, which is the material with the pebble dash on and that rather horrible plastic finishing moulding on that's coming away. Ideally, the eaves where the guttering is would be extended out so that they extend over the level of the insulation. And you don't have the risk of water dripping down and getting behind the insulation layer, which is exactly what happened here. And it just means that the wall behind the insulation gets soaking wet. The insulation prevents it from drying out, and therefore it migrates back into the house. So you ended up with terrible damp problems on the inside of the house. That led to very high levels of humidity throughout the house, and then one thing led to another. You've got mold all over the place, damage to the plasterwork and the brickwork. Everyone had to be moved out, and horrendous costs for repairing all of this. You know, removing all the insulation, repairing it internally and externally, and costs of rehousing people. You can imagine it just goes on and on. And it's these kind of failures of projects which basically led to the Each Home Counts review, and that recommendation that report is really what led to PAS 2035 and Trustmark being adopted as a kind of retrofit methodology and quality mark for workmanship. So basically this is I believe another part of the same case study. So yeah, really trying to think about all the costs of not just the repair costs, but the damage to people's lives, their health, their upset that their homes have been ruined in this way. And it adds up to an enormous amount of disruption and damage and upset and cost. So basically to be avoided. Okay, so I hope that was informative.